Okay, second half of 6-1. Okay, guys, this begins on page, the bottom of page 508. Some of the components in physics that we can, well, I should have said it this way. Some of the aspects of physics that we can componentize, that is, vectorize, I guess, are things like velocity, it's a vector. Acceleration is a vector. Force is a vector. Things like that. We're going to be discussing those things, kind of physics involved, except for number 8, which is strictly navigation. Right off the bat here, on example 7, the author is very, very confusing, and I need to straighten you out. It's not the words, it's the picture to the left. Whoever typeset this thing decided that it would be a good idea to put the picture of an airliner in there, and they thought, let's just line it up with the vector. Very, very confusing. In example 7, I need you to fully understand this. In the picture on the left that they draw for you has nothing to do with the takeoff angle of this jet, but they lead you to believe that by that simple picture. Forget that that plane was ever drawn. What you're looking at there is a picture of a compass. In other words, a bird's eye view. The airplane's right here, and he's going to take off in this direction. We don't care how high he is or what angle he takes off at. That has nothing to do with this problem, though it is very misleading in the picture. We're talking about the direction he's headed, not the angle he took off. Totally different things. So we're talking about direction here, okay? So forget that that little airplane was ever even drawn on that picture. So here's what it says. A DC-10 is flying at a bearing. So as soon as you see bearing, you're talking about compasses. It's flying at a bearing of 65 and going 500 miles an hour. Right there, folks, that is direction and magnitude. We got vector information. Okay? Here's what we're to do. Find the component form of the velocity of the airplane. That's not very hard to do, but we got to put it together. Recall that the bearing is the angle that is the line of travel it makes with due north, measured clockwise. So you have to do things properly. So we're to find the component form of this vector, and the first thing we draw is according to a compass. If this is north, or our positive y-axis, and this is east, when they say that it's taking off at a bearing 65 degrees, they mean this angle right here. Right? I don't know if you remember me telling you this yesterday, but I'll tell you over and over and over again. When you do things and calculate and use component form or ij form of a vector, anytime you do anything with a vector, you have to create your angles to go from the positive x-axis counterclockwise. So we draw this one according to the bearing they gave us, and then we componentize this thing with this angle, which would be what? 25. This is our angle, but it came from this one, but still, we're not going to use 65 in our calculations. How long is this? 500, that's the length of it, or the magnitude of the vector. And what we want to do to accomplish what they're asking us to do in this problem is to find this component form. And component form is always based on this angle with the x-axis and a counterclockwise move. But how are we going to do that? Well, do what we've always done. Make a triangle by dropping to the x-axis. All right. I'm going to change this because I'm going to need more room to write than that. But that's what we're after, is the component form. How far is it from here to here? And don't give me a number. How far is it from here to here?
Sine 25. The cosine 25 over 500. No, cosine 25 equals
Cosine 25, I'll buy that, but that's not all.
500 cosine
500 cosine 25. That is our cosine theta.
Wait, can you explain that?
Well, hold on. Just cosine 25 equals x over 500. 2 times the 500.
Oh, okay.
Yeah.
Oh.
Okay, does anyone else need that explained further? Yeah, I figured. Okay.
It's okay.
If I want to know how long this is, and I call it x for just a minute because it's along the x-axis, then in this triangle that I've drawn, the cosine of 25 is x over 500. And so x is 500 cosine of 25. Yeah? We good? So if it's from here to here is 500 cosine 25, that's the x value of the component form of this vector. That's the x value of that point, in other words. So 500 cosine 25, comma, what would this be without figuring it out?
500 sine.
Good. 500, ooh, got a little period away with my zeros there. 500 sine of the same angle 25, because this would be y, and the sine of 25 is y over 500 cross multiply, you get 500 cosine or sine 25. Besides that, we have learned that points in this grid written in trig form is always cosine sine. R cosine, R sine, basically. You okay with that? Everybody good? No, that's what you have to figure. They want the actual numbers, but this is how you would figure it without having to do all the trig from basicness. You guys be sure you're in degree mode to do these problems. Probably already are, because I mean this chapter is a lot about degrees. So we get 453.15. And what? 211?
0.31.
211.31?
Yeah.
Okay, so what that means is for about every 450 miles you go east, you also go about 211 miles, 210 miles north. As you travel along this, it's in that ratio. That's what's going on. But this was what they expected, the component form. And let me reiterate just really quickly, they gave us navigational directions. We have to convert it to an angle made with the x-axis and counterclockwise. Then we use that angle and a right triangle to write the x value, or in other words, the horizontal leg and the vertical leg in this form. Figured out, that's the component form. You could also write it in IJ form really easy if they ask for that. Right? Okay, that's example 7. And that airplane in it makes it very confusing, so pretend it's not there. All right, example 8 gets a little more complex. Still in an airplane, but we've got to get to a destination, and we've got sort of kind of crosswind, which means we got two things affecting us: the direction and speed of the airplane, and we also have direction and speed of the wind.
So that is going to be two different vectors.
Yeah.
We're actually considering
And the two combined, and the word combined here means add. The two combined give us some sort of resultant vector. But you got to think about this. If she's going to land where this woman's going to land where she's supposed to, she's got some figuring to do. Listen up. Shh. Pilot Megan McCarty's flight plan has her leaving San Francisco International Airport and flying a Boeing 727 due east. None of that is important to what we have to do, but gives context.
but do we?
Now starts the information. The next sentence gives us information we're going to have to use. There is a 65-mile-an-hour wind with a bearing of 60 degrees. Find the compass heading McCarty should follow and determine what the airplane's ground speed will be. What does that mean? What is the difference between ground speed and airspeed? Does anybody know?
Like the airspeed would slow down the airplane, so when it's actually moving across the ground, it's moving slower
Kind
than
of.
it actually
Yeah.
reads.
Ground speed is the actual distance it's covering from one destination to another. Airspeed has to do with how fast it would be going if there were no wind. How fast it, and airspeed could be more or less than ground speed, depending on whether you have a headwind, which have an airspeed higher, believe it or not, if you have a headwind. Because the airspeed in still air would be more than it is with the wind beating on you.
Yeah.
So the airspeed in still air is more.
So the airspeed is how fast the air comes and hits the plane?
No,
Basically?
no.
No.
Airspeed is how fast the plane would go if there were no wind hindering it.
Yeah.
And if it's got a headwind, it's going slower. So ground speed would be less than airspeed.
Oh, yes, that makes sense.
Okay. If it has a tailwind, now your ground speed is more than your airspeed because you get a little help. If you got a crosswind, you may get some help and some hindrance. Believe it or not, and I know you guys think I'm nuts, but I'm always looking at the weather and figuring out how fast the wind will be and which direction it's going to be coming from to know about how long it's going to take me to get home. I've ridden enough to know. And tonight there's going to be an east-southeast
You're
wind.
joking.
I'm not kidding.
You're
And-
awesome.
On
And
your
east,
right?
I don't figure it to the minute, but I know that So winds of certain speeds at certain times is gonna take me longer to get home by a few minutes, or it may help me out. I'm always looking for a south wind I'm always looking for a north wind in the afternoon, which never happens.
Yeah.
And I'm always looking for a south wind in the morning, which never happens, because in the evening, the cold air comes down off the hills and blows this direction. So I'm always facing a headwind, almost always. So I need to live in sugar and teach in medicine, and then things would work out.
There we go.
Anyway, so tonight, I just looked it up just now, just before I came over here to teach. Tonight, I'm going to be facing, if it's right, when I'm headed home, I'm going to be facing a wind that's going to be east-southeast, which is almost exclusively east. It's more east than south, so it's going to be coming in like this, and I'm going to be heading up the highway like this. So it's going to hinder me, but not as much as this one would have. You know what I'm saying? Yeah, thinking vectors. And it'll be at about 9 miles an hour, which is not really detrimental. If I focus and not lose my focus by listening to my story too much, if I focus on getting going, I can usually, it's negative. But if it's a, 15, well, more like 18, 20, 25 mile an hour wind, I just got to settle in and keep pedaling. It's hard. I don't like it, but I do.
Ride your motorcycle.
Have you ever almost been hit by a car?
Motorcycle's leaking gas.
It has been hit by a car. You've been hit by a car?
Twice.
On your back?
Once almost broke my leg, and the other one broke my arm.
Did you break them after they hit you?
No, but what was really
She
funny
gets
is
up, she's like.
the second time I got hit by a kid that I used to teach when he was 10 years old in Sunday school.
He's like,
And he was kind of in shock, and the police came up, and all he kept saying was, he just kept whispering, I hit my Sunday school teacher. And the weird thing was, he was driving a white car, so it was pretty evident. But I used to have slime in my wheels. I don't anymore. I figured out a better way to avoid punctures. But I had slime in the wheel, and he hit me right in the back and busted my back rim really bad and popped the tire all over. Slime's all over his car, all over the road. It looked like he hit an alien. It was horrible. That slime's green, and it's sticky and gross. But anyway, it was really crazy. Anyway, so we're talking about vectors on things that hinder or help your flight. Listen to what's going on here. We realize that this lady is likely to be blown off course by this rather minor wind. Usually the wind's a lot more severe. She's going to get blown off course. And so what we are going to try to do is to figure out how much she will have to adjust her course into the wind so that she will land where she wants instead of just let it blow her off course and she lands, 200 miles from where she meant to. We're trying to figure out the vector she will have to adjust to by adding the vector as though she were flying the plane without wind and the wind vector. We're going to add those two together to get a resultant that will get her where she belongs. And this is harder than you think. All right, so let's try it again. It says, the first thing we find is in the second sentence that's useful to us. It says, there is a 65 mile an hour wind with bearing 60 degrees. So I'm going to draw the wind vector. Bearing 60 degrees is about like that. And we're going to use this 30. And if I just arbitrarily draw this and put an arrow on it, this is my wind vector, and it is 65 units long. Because it's going 65 miles an hour in this direction.
Right.
Yeah. Okay. Here we go. Let's see what we got here. It says, find the compass heading McCarty should follow. And determine what the airplane's ground speed will be. Assuming the speed with no wind is 450. That's her airspeed is 450. So we got to figure out her ground speed, and we have to figure out what direction she should take so she lands where she wants to. Okay, so if the wind is blowing from right here when she takes off, if the wind is blowing like this at her, what's going to happen if she just lets it blow her off course? Which direction will she be headed, do you think?
Push her over.
Well, east.
Maybe just west.
Hold on, where's the plane going? Where's the
Isn't it going to east?
I don't know. Is the plane going due east?
Yes.
Yeah, so it's going to push her like north because it's under the wings.
If she's headed east, it will push her north. But is she headed east?
Yeah.
Is that what it says?
San Francisco.
So she wants to head east. I think I've got this backwards in my own mind. Hang on. Oh, yeah. So she wants to head due east, And if she does that, as Cash just said, if she's headed this direction and we let the wind just take her off course, it's gonna blow her this way a little bit, right? The wind isn't nearly as fast as she's going, so it won't blow her as she's going. So it's not going, it's not gonna blow her very far off course, but it will blow her off course. And if she's headed to this town over here, she's gonna end up over here if she just lets it happen. So that means she needs to head off in a direction like this in order for the wind to blow her onto the course she wants. You see that?
Oh, yeah.
We got to figure out what this is and how long the resultant, which would be this vector. This is the resultant vector here. You're going, no, sir, that isn't what you said. Yes, it is. Just hang on. The resultant vector wants to land her on this path right here. And keep in mind, this is totally and completely out of scale. If I let her, or her airspeed vector be this, that's the direction she's going to head off, so it'll blow her back on course. This is how long? 450. Now, she wants to follow this path, right? Okay. So do you understand that this wind right here that we've got is going to blow her off course a little bit this way? If she heads out this way, it'll blow her off course, so she has to adjust this way. But it's also going to push her along a little bit because it's a little bit behind her, mostly behind her, actually. This component's longer than this blow off. This will blow her off course. This will push her along, this part of it. That's why components are really nice. It will push her however long this vector is, and it will blow her off course however long that vector is. It won't be 65 miles an hour in either direction. It'll be a piece of it. So this is the resultant vector, and what we wish to find, if you think about this, is if I move this 65 vector to add the two together, the 65 and the 450 vector, if I move this vector down here in such a way that it lands us right there, this is her resultant vector. That's the vector she wants to follow. If I add the two together. Okay? So we move that vector down. Boy, I didn't move it very well. Let me bend it just a little bit harder so it looks a little more parallel. Does that look better? It's not either.
Parallel.
What I'm going to have to do is just pretend I moved that around. Because it's really hard to draw these at the correct length so that when you move it down, it actually lands on the x-axis. Just pretend it's the same one. This is 65. I moved it down. Now, here's what I need to do. I need to figure out her ground speed, which is the length of this resultant vector. And I need to figure out how much she's going to head off this angle right here so that she will be blown onto this vector here. And we do it by adding this vector, which we don't know. Well, we know its length, but we don't know what angle. And adding it to this one to get a resultant vector, which is this one. And we do know something about this resultant vector. What is it? We know that this one is 0. Must be. If she's going to end up going due east. You following?
It's on the x-axis.
This vector right here is on the x-axis, which means its y-coordinate is 0.
What did you mean? 450.65?
No.
Oh.
Can't just add the lengths. When you add vectors, you add x's to x's and y's to y's. Right?
Yeah.
Okay. So this is the way that the book would like you to do it. I will do it 2 different ways and show you. You can pick which one you want. But the book wants you to get a vector form of this one, a vector form of this one, add the two together to make this one, which you can do, believe it or not. Okay? What is the vector form of the wind?
It's 65 cosine.
You guys are catching on. That's good. Whoops. 65 sine 30. Remember, you're using the 30. Okay, those have numbers to them, which I'll write down in just a minute. You guys figure it out. Well, let's go ahead and do it. What's 65 cosine 30?
56.29.
And this?
32.5.
We knew that because the sine of 30 is a half, and half of 65 is 32 and a half. Okay, so we didn't know that. Okay, so those are the values that go with it. We use the trig to figure it. Now, what do you know, if anything? What do you know about this component of this one? This, where she's got to head off.
Oh, it's 450.
Cosine negative theta.
Just theta.
Just theta? That might not negative theta.
We can do just theta. We'll have to reconcile it. I realize, I understand why you did that because it's dropped down. Is it gonna be that? Let's see. Cosine will be this, which is positive, yeah, it will be the cosine of theta. And then,
What a fool.
Five sine theta.
450.
450 sine theta, but negative.
Okay, well, how do we know?
Because,
Because it drops down.
yeah, because the y value drops down as negative.
And theta is positive.
If you use this right triangle right here, and theta being positive, and this is positive, this part is negative. So if you're actually gonna use the angle theta, you have to make this a negative because it's below, it's a negative drop down. Y'all following? Okay, so now what? This y component added to this y component has to equal 0. So we don't know anything about the x, but we know that the y must be 0. So we can make it, we can write an equation as part of the adding of this vector to this one. See what I'm saying? So we know this, that 32.5 added to, well, subtracting 450 sine of theta must equal 0. You see that? Y'all adding vectors, at least this piece of it? Which means that 32.5 divided by 450, inverse sine, that's the sine, must be theta. Now, did you follow that algebra, or do I need to go slower? Y'all understand that? You see the algebra or not? Because I can go slower if you want. No, the theta. What does theta turn out to be?
It's a double negative.
Which makes it all be.
I did it right.
4.14.
Really? Degrees? Yeah, 4.14 degrees. You're right. So this thing is way out of scale. You guys are all in degree mode when you gave me the 4.14, right?
Yeah.
It's not radians. So the reason why this angle is so tiny is because she's going so fast and being blown off course by such a small amount, really blowing off course only by 32.5 miles an hour, because this is the only part that's affecting that. That's how long it is. This is a very tiny angle. So we've got the angle. That's one of the things they wanted. But they also want the component form of the resultant vector. So we got to find that. How are we going to find that?
4.1 or 450 cosine 4.14.
450, and I'm going to say cosine answer. I'm hoping it's still in your calculator. 450 cosine answer.
448x. 448.8.
I don't want that yet, but I'll take it in just a minute. But I got to add this to what? To the 56.29. If I was being really careful with accuracy, I would say to 65 cosine 30, so that I'm not approximating. And that will be the x component of that vector. 505 point miles per hour.
Wow.
So she is getting a lot of help. She's burning her fuel at a rate of 450 miles an hour, but she's actually going 505 miles an hour because the wind's helping her out.
Say the environment.
So this angle was one of the things we were after, and this vector, I think, was the other one. Was a vector or how fast? No, that wasn't it. They just wanted to know what her ground speed was and what the angle she had to take off at.
You're starting at the top, coming down.
So once you have to add
90
that,
plus that.
90 plus this? Oh, yeah, you're right. Okay, the theta in our picture is 4.14 degrees, but that is not the bearing. That's what they want, is the bearing and her ground speed. Ground speed is 505.12 miles an hour. Y'all understand that? But the bearing is not this. You're right. It's 94.14 degrees. That's the bearing. And this is the ground speed.
Because for bearings, we start.
Yeah, bearings have to go. You have to return to the bearings, which is north clockwise. And it's 90 to there, and then another 4.14.
Oh.
Did you catch all that? That's quite a problem. That's hard to do. You'll have access to this video if you want to watch through it again. Took a little long. Okay, the last thing looks deceptively simple, and it is not. You gotta do some thinking that you may have never done before. It's not hard, but it's new, which makes it a little difficult. And I want you to understand some physics, so I'm gonna be doing this problem slightly different than the author does. You're welcome to do it his way if you want, but he leads you blindly through it, and you just have to take it on faith. And I want you to try to understand a few things. So here's our deal. It says a force of 30 pounds just keeps the box in this figure from sliding down the ramp, inclined at 20 degrees. Find the way to the box. Now here is an assumption that we always make in elementary physics. There is no friction between the box and that inclined plane. That's the assumption we make. Obviously there's friction. We will not account for that. If we had to account for that, this would take a couple, maybe 8 or 9 days.
What?
To convince him about things like static friction and kinetic friction and when one becomes the other and by how much, and we're not doing that. Okay? So, to simplify the problem, even though it isn't real, people go, nothing's real. Yeah, well, it's to make your life simpler, so buck up and take it. There is no friction between the box and the inclined plane. Imagine that. And it would be more like having an inclined plane made of those little tiny steel rollers like this, that are really close together. That's almost frictionless. Pretend that's what we got going, and there's no friction. And so you put the box on there, and it immediately starts to move unless you hold it. If you hold it somewhere or another, or put some force on it, so that it's also you're not pulling so hard that it begins to come back up towards you, but you're also not letting it go down. It's called static. There's an entire course, 2, I think now, in engineering called statics. I just helped a kid get through it. He comes in, he just finished up at BYUI. And he was taking a statics course. And it's an entire course on what forces and in what combination do we have to keep something still. Like hanging a sign and how much tension is in each chain. Or there's all kinds of things that we want to just keep still, and we got to apply the forces at the right angles and in the right amounts so that the thing doesn't move. That's what we got going here, the statics problem. This box is stationary on that inclined plane with no friction between the box and the plane. That means somebody's pulling up the ramp in just the right amount of force so that it doesn't pull towards them, but it also doesn't let it drop. Do you understand? Yeah. Okay. So if you follow that, it says a force of 30 pounds just keeps the box in this figure from sliding down the ramp. So that's the up the ramp force, 30 pounds, to keep it stationary. That's a force, that's a vector we need to take account of. It's a force vector. Okay. It is inclined at 20 degrees. Find the way to the box. That's all they're giving us. Happily, it is enough if you know what to do. So, watch this. This picture.
You'll always be in a blind.
This is 20 degrees right here. They gave us that piece of information. Here's the box. Well, I'm not going to actually draw the box. Here is the center of gravity on the box. That's where everything is attached to a single point, so we can simplify things a little bit that way too. And this is a vector pulling it upward. Parallel to the ramp, pulling it that way with a magnitude of 30 pounds. Our task is to figure out how much the thing weighs in pounds. You're going, what? Yeah, I agree. What you've got to do is draw the vectors that are keeping this thing from moving anywhere. What vector is keeping this box right here from just starting to float up off? Gravity is not a force. Gravity is an accelerator. And that's another thing in physics you'll learn pretty quick. The thing that keeps the force, and it's really important that you get straight in your mind what forces are and what accelerators are and stuff like this. Everybody else says the force of gravity. It's not. It's the force due to gravity, which is called weight.
The weight keeps it.
Weight is the force. And weight is what is the force that's keeping it from just floating off into space. That's what we want. And weight acts directly straight down, perpendicular to the ground, to the center of the earth. That's how gravity acts. The single point of the center of the earth. So this is going to be perpendicular to the ground, which we raise the ramp up off of. You with me? So this vector right here, as it comes down, has to be perpendicular to the ground. And this is the weight vector that we seek. Now, here's a tricky one. This is one people always, this is the new thinking that's really bizarre. There is yet another vector, force vector, that keeps this box from sinking into the ramp. Because it's being pulled down, right? What the heck is it that keeps it from just being pulled down into the ramp towards the center of the earth forever? Yes, I understand what you're saying because this is the way you're thinking. It is the rollers. It is the ramp. It is the stiffness of the ramp. It is the support of the ramp. But that ramp is acting in this direction to keep it from sinking. This is called the normal force. Normal is Latin for perpendicular. Perpendicular to what? The ramp. There are three forces acting on this to hold it still. There's the guy pulling it up the ramp, there's the ramp keeping it from sinking, and there's the weight keeping it from floating away. All three of those act to keep that thing still.
Don't you have to have the vector going that way too to keep it still? Because you have to have pressure against it.
No, because then you were putting pressure on this. That's all accounted for in the components of this one. Components. Okay, so here's the deal. Here's what's always the deal in statics. If you can identify all the vectors that are acting on it, if that thing is not moving anywhere, then they must all add up to zero. Right? Okay. So under those conditions, let's see what we can do to draw a picture that will show that they all add up to zero. Now, keep in mind, I freehanded all of these, which means they may not be the same length when I'm done. Just go with me. If I take this force acting up the ramp and I pull it down here so that its tail is on this one's tip, that is geometrically adding the weight to that vector, that pulling vector. Okay, so I'm going to move that down to here like this. And I may have to, yeah, I'm really going to have to cut that short. Okay. It needs to be about this long. So let me cut it down up here. Freehanding is always dangerous. That's the 30 meter vector. So that's 30 pounds right there. And then if I take the normal vector and take it and keep it pointing in the same direction, everything like that, and take it and move it down so that its tail is at this one's tip, then when I draw it, this one, the normal coming in, it had better return to there because they have to all add up to zero. It has to end where it began if it's going to add up to zero. Does that make sense? Here's my normal vector. Here is the 30-pound vector down here, and I've moved them all in such a way that they will all add up to zero. In other words, they will be, this last vector that I had will end where the first one started. That's what statics does. So if I move them all that way, now, so I've got this triangle to work with, and we all like triangles. We're very familiar with them. Now what? First of all, do you remember that the normal vector had to be perpendicular to the ramp? So this is a right angle. That means this is a right angle. Does that make any sense?
Oh, yeah.
What is this angle?
20.
It is 20. How do we know that? Because if you take this vector right here, the weight vector down like this, and you hold it like that, as you raise this up, that vector swings this way the exact same amount. Does that make any sense? Why this has to be 20? Okay, so if you have something like this, and it's horizontal this way, and you've got something coming down to it this way, anchored right there. As you move this up, that thing has to swing out the same amount. You move it up like this has to swing out the same amount. Can you imagine that? This is some physics involved here. If it's attached right here, well, I shouldn't say anchored right there, but that thing's got to swing out this way. As if you move this ramp right here up 20 degrees, as you move it, this one's going to swing out 20 degrees. Does that make any sense?
Yeah.
Okay. So this has to be 20, and that's where we're getting this from. Don't just say, yeah, that looks about 20, so I'm thinking that's it. No, there's an actual reason. That one's 20. So now we've got an angle. We've got a right triangle because of the perpendicularness of the normal. That gives us a right angle. And we have a side. We can find anything else out that we want. And what we want is weight. So what ties together that 20 and that 30 and that W? Sine. That's what you have to figure out. So, but it's important that you be able to draw the vectors to form a triangle that completes itself and also has a right angle. The normal vector will always provide the right angle. That's really nice. So when we look at that triangle, the sine of 20 is going to be equal to 30 over W. And so W will equal 30 divided by the sine of 20. What is that?
It's about 87.71 pounds.
Okay.
That's what I got. That's what the book says.
81.71? Is that what you said? Okay. Pretty heavy box. 87?
87.71.
So that's a pretty heavy box when only 30 pounds holds it stationary even if there's no friction. But that's because you're not raised up very much. If you were trying to hold that box stationary on the side of a cliff, then your vector would be equal to the weight, or it wouldn't be holding still. Those would be the only two things. If this was the cliff and you're trying to hold the thing from dropping any farther and you're holding it still, your support vector and your weight vector would be exactly the same. Otherwise, the thing would be either falling or rising, right? And as you lower that angle, infinite, as you lower that, not infinite, but the slope is infinite. If you lower that angle down, this becomes shorter and shorter and shorter until it's pointing out that way at 30 pounds. You see what I'm saying?
Yeah.
These are tough at first, but that's the kind of picture I would like to see. Because when you hit the physics class, having already experienced this is going to be easier for you. You need to add up the vectors, and there's always, well, in this situation, there's always three. Something keeping it from sinking, something keeping it from floating away, and something keeping it from sliding. And you need to draw them all and add them up. Okay? All right. So, the second half is that's Simon Given. Get after it. Do the best you can. See ya.
Yes. The lights go